This part of the lesson will deal with how the aeroplane's takeoff distance is actually calculated. Shown on screen is an example of the takeoff performance information. The example graph we will use is figure 3.1 on page 3 of section 3 of CAP 698. Firstly, the title of the graph indicates that the graph is for calculating takeoff with normal procedures. For other procedures, like maximum effort takeoffs, you may have to consult another graph. Next, take a look at the associated conditions, paying particular notice to the power and flap settings, as shown here. Also notice that this graph assumes a runway that is paved, level, and dry. If the conditions required for a given calculation are different, corrections will need to be made to the values that this graph will give. We saw these correction factors earlier. Notice the liftoff and obstacle at speeds. In this case, the obstacle at speed is the takeoff safety speed. A pilot must adhere to these accurately because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would actually not be achieved. Having looked at the various bits of information around the graph, let's now examine the graph itself. In the example, we will assume a temperature of 15 degrees at an airfield which is at a pressure altitude of 4,000 feet. To use the graph then, move upwards from 15 degrees until you have reached the 4,000 foot pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass, or weight. In our example, let us assume a weight of 3,400 pounds. From the reference line, we must move down using the sloping guidelines until we reach 3,400 pounds, as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize the 150% tailwind and 50% headwind rules that you have learnt about in the general principles for takeoff have actually already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more, up to the last reference line. Remember that the takeoff is not actually complete until the aeroplane has reached the 50-foot screen height. So from this point on the graph, we must move up the guidelines to the end. The takeoff distance in our example is approximately 1,550 feet from brake release to the 50-foot screen, and the takeoff roll, or ground roll, is 1,250 feet. However, let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the takeoff distance. Since the graph assumes a paved dry runway, we will have to make a correction to the takeoff distance for the different conditions. You may recall that wet grass increases the distance by 30%, or by a factor of 1.3. Our calculated takeoff distance was 1,550 feet. But correcting it for wet grass would now make the distance 2,015 feet. Let us now assume that the runway has an upslope of 1%. You may recall this would increase the takeoff distance by 5%, or by a factor of 1.05. This now makes the total gross distance 2,116 feet. To comply with the regulations, you will recall that the takeoff distance must be compared to the available distances at the airfield to ensure it does not exceed the limits laid down by the authorities. To remind you of these regulations, turn to page 1, section 2 in CAP 698. The remaining pages in the multi-engine takeoff section of CAP 698 are the takeoff distance graphs themselves, and various examples on actually how to calculate the takeoff distance or maximum permissible mass for takeoff. There are also some graphs for calculating the accelerate stop distance required. Although the accelerate stop distance graphs are shown in CAP 698, there is no requirement for a multi-engine Class B aeroplane to demonstrate performance accountability of engine failure below 300 feet, and therefore there is no requirement to demonstrate the accelerate stop distance. However, a prudent pilot will check the accelerate stop distance required by the aeroplane in the event of an abandoned takeoff so that it will be shorter than the accelerate stop distance available. On page 2, section 3, is an example you may follow to calculate the takeoff distance. Page 3 of section 3 is the takeoff distance graph, but without flap, which we have already used and worked through. Page 4 of section 3 describes how to determine the maximal permissible mass to meet all the regulatory requirements, an example of which is on page 6. Lastly, on page 7, we find another takeoff distance graph, but this time assuming a maximum effort takeoff, which uses a higher flap setting. And on page 8 is the corresponding accelerate stop distance with this higher flap setting. You use these last two graphs in an identical way to the one you have already worked through. You will need to practice using all these graphs, so ensure you work through the examples in the CAP 698 and those in the questions for each lesson. Doing this will help you improve your accuracy in the use of the graphs and help to consolidate your knowledge of the principles we have considered so far. The last part of the lesson will focus on some of the certification specifications for multi-engine Class B aeroplanes. These can be found in the EASA document CS23. There are only two main specifications that apply to the takeoff phase of flight, and these specifications concern the takeoff speeds. The first of these certification specifications concerns VR. The specifications state that for twin-engined land planes, VR must not be less than the greater of 1.05 VMC or 1.10 VS1. VMC is the velocity of minimum control, which means the minimum control speed with the critical engine inoperative. VS1 means the stall speed or minimum steady flight speed obtained in a specified configuration. The second of the certification specifications concerns the speed of the aeroplane at the screen height. The specifications state that for twin-engined aeroplanes, the speed at 15 meters or 50 feet above the takeoff surface must be the highest of three speeds. Firstly, a speed that is shown to be safe for continued flight under all reasonably expected conditions, including turbulence and complete engine failure. Secondly, 1.1 VMC. And thirdly, 1.2 VS1. The certification regulations concerning VR and the takeoff safety speed are not found in CAP 698 and therefore must be committed to memory. This completes the lesson on the takeoff for Class B multi-engine aeroplanes. Familiarize yourself with the format of the aircraft you are flying and correctly adjust the calculated takeoff distance for any variable that is not accounted for in the data. An understanding of the various conditions and factors that control the takeoff will better equip you to ensure that all your takeoffs are well within the limits of the runway available. In this way, you will minimize any chance of an accident occurring. Lastly, do not forget to check the regulatory requirements for the takeoff distance of the aeroplane you're flying.